Okay, okay. Please let me inform you about the webinar terms. The headphone will be shut down to about interruptions. In case you have any question or comment during the presentation, we will proceed the following ways. In the lower right corner of the menu, choose the activity option and then the question answer button. Once it has been formulated, we will answer it during the interval for this purpose. Okay, all the questions we do not answer during the webinar, we will do it by email. And in case you have questions after this webinar, you can get in contact with us to our following email address is info@group-sa.com. Now, let me introduce you the professor and pharmaceutical degree Arturo Oya, in charge of the dissertation. Mr. Oya is a very expertise pharmacist with large experience in R&D and production area, with more than 30 years of experience in Pavo laboratories as a prominent pharmaceutical company among others. It's a pleasure, and with me will be a great benefit to listen to him carefully in his exposition. Please, Mr. Arturo Oya, is your moment.
Thank you, Daniel, for introducing me. And good morning and welcome everyone, and thanks for taking time to hear our third webinar about pharmaceutical technology of solid dosage form. Today, the webinar will give an overview, a general overview of the direct compression line. And let me share with you the presentation. Please let me know if you can see the presentation.
Yes.
It's okay?
Yes,
okay.
Yes.
Okay. So, well, as you know, in general terms, obtaining tablet through direct compression is the most convenient way for various reasons that we will see immediately. It is the procedure that we all would like to use. And so the formulation team, the Galenic, start out administration, the formulation by a direct compression tablet. We have the raw materials, and the raw material will be transformed in the semi-finished product or intermediate product. And this intermediate product must be a blend of different components, the API and the excipients, with good uniformity of API, with good flowability, with good compactability and density. These are the attributes that the blend has to have to good performance in tableted machine. Well, our vision, our approach is that the procedures need to proceed with efficacy and efficiency, and the quality of the product must be the best. This is the idea we have, and all the efforts are conducted to obtain quality of product, but efficiency too. Both things are important. Well, remember that the API and excipient are transformed in the intermediate product, the blending to tableting, then tableting in the tablet press, and then coated. This process we will study in the next webinar, but now let's remember the technologies for produce the intermediate product, blending or granules. This table have showed the general process, the direct compression powder, the dry granulation, the wet granulation. Wet granulation was presented the webinar before, and dry granulation will be the next webinar, the fourth webinar. Today, we will focus in the direct compression powder. The most important operation here is the blending. The blending is the main unit operation in this line, in this direct compression line. And this blending is possible to be made in tumbling blenders or in convective blenders. So we will speak about these different ways. Well, this is an important slide because show us that the wet granulation today is the most important way to produce, to elaborate the intermediate product. And the second alternative is the direct compression. Of course, all of us want to produce by direct compression because all the advantage that this methodology has, but not always is possible to obtain the intermediate product with good attributes by this way. This is a survey, actual survey, and now I want to show you the complete line of direct blending, direct compression. These are for equipment, for machines, in order to produce by direct blending. The API and excipients are milling by the conical mill in order to broke the lumps, the aggregates, and including adding to the blender. In this case, this is a IBC blender. We will speak about this in a moment. And when the blending is end, then tableting in a high-speed machine, and the tablets are coated in the pan coater. Okay, this is the central unit operation, the main, the most important unit operation in the direct compression line, the direct blending, where the powders are not binding each other, but are free for movement. This is a typical characteristic of the blending, the direct blending. Well, but direct blending has a lot of advantage and have some disadvantage. I want to show you some advantage and disadvantage. For example, of course, the simplicity is the most obvious. The short time process, because it has less equipment, less number of unit operation, less physical stress and on the raw material. This is a very important question, because when you wet a powder, you can produce, in occasions, hydric stress, hydrolysis, transformation in crystals, transformation in different polymers, etc. And then you have to dry in fluid bed dryer, so you can introduce thermal stress or thermal stress. So this is the advantage in the direct blending: less physical stress on the raw materials, less risk of instability, of course, less energy costs. Also, you have better tablet disintegration, because you have to broke the tablet, but not to broke the granules, because you have not granules, you have particles, simple particles. So better tablet disintegration impact in API dissolution. And this is very important in the case of course, of immediate release product. You have lower probability of microbial growth. This is due to the low level of water activity. So this is a very important question. You don't need to protect, because the powders are with low activity, so the possibility of microbial growth is minimum. Of course, less equipment and less cleaning time, so you reduce the downtime, you reduce the qualification and validation of the equipment. You don't need training staff. Is reducing the staff training, and you need reduced facilities, because you don't need technical area. Milling equipment, blending equipment, tableting equipment, and coater are in specific areas. Well, but of course, blending, direct blending has disadvantages. For example, the cost of the raw material is higher than the typical granulation. Is hardly applicable for products that have this characteristic. When the product we want to produce has high dose of API with bad properties of flowability and compactability, well, we have a problem, because direct compression could fail in these cases. Of course, you must try to obtain a good direct, but it's difficult to obtain. The other question is when you have low or very low doses of API. In this case, it's not a problem of flowability or compactability. It's a problem of uniformity. The uniformity of the API in the blend is very difficult to produce a uniform distribution of the API when the API is 1% of the total or 0.1% of the total. And you have another problem. Let's suppose you obtain a good uniformity in the blend, but then it's possible that the API segregate from the rest of the component in certain measure, and you have another problem, the segregation. So these are disadvantages that the direct blending has. Risk of not complying with content uniformity specification, and the risk of API segregation. Of course, you have greater sensitivity to environment relative humidity, increase the probability of capping because the level of content of humidity in general is most frequently the capping in direct blending compression than in the granules. Of course, the pollution with the fine powders, because you manage powders in which the size is in the order of less than 100 microns. It have the more difficult to tablet coloration, and is possible that you have higher batch-to-batch variability. Well, this is a general table that show the advantage and disadvantage of direct blending. In general, we say, well, advantage are a lot than the disadvantage. Well, but we always say the quality of the product and the process efficiency depend on the technology? This is an important question, but in our vision, beyond the technology, the quality and the process efficiency also depends on the particular solutions. For example, the quality and the efficiency depends of technology, but depends of these two factors too: raw materials and formula, and manufacturing process per se. For example, the solution when we speak about raw material are a good selection of raw material is very important. Define the purchase specification of this raw material, the quality and quantitative composition of our formula, tips of formulation, of course, the expertise you have in the formulation. For the other hand, the manufacturing process needs a good configuration of the production lines. To define the setting of process variable, the problem of the scale up, of course, specific application, or methodological tips that enhance the expertise. So what we want to say is that the quality of the product and the efficiency of the processes are dependent of this trilogy: technology, raw material formula, and manufacturing processing. Okay, now I want to say that because the blending unit operation is the most important, so we will speak about the blenders type, the first of all. And here you have the tumbling blenders and the convection blenders, the great classification. You can see in SUBAC manufacturing equipment addendum guidance from the industry. You will read this in Google. You can see the classification and definition of this type of the machines. Well, tumbling blenders are the blender whose container rotates around the axis. The typical type are double cone tilted, cubic, V-shaped, and BIN, the IBC technology. You have this equipment with or without internal intensifier, because in occasions some type of powder need to be to use intensifier. But these are the typical tumbling blenders, and the basic mechanism of blending is the dispersion of a particle, but in these cases the share is very low. So this type of tumbling blenders, the rotary blenders, are ideal for free-flowing powders and are not ideal when the powders has cohesive properties, very cohesive properties. Well, for other hand, the convection blenders are fixed. The bowl or the container is fixed, and an impeller into the bowl move at high speed, let's say 100 RPM or 200 RPM, and this produce another type of mechanism of blending. Typical equipment: ribbon and powder mixer, Sigma blade, planetary, and the most common and modern and efficient, the high shear mixer granulator. The same that we speak about wet granulation the last webinar. High shear mixer granulator, horizontal type like MIC of pad group or Diosna or Collet, and the vertical type like Lodich. In this case, the basic mechanism are convection and high shear. So the flow that creates in the impeller let the powder with a good mixing, and in this case is ideal for highly cohesive powders. This is the big difference between tumbling and convection. Here, additional information. For example, tumbling blenders, the powder mixing is tumbling blenders take place as the result of particle motion in a thin cascade layer at the surface of the material, while the remainder of the material below this layer rotates the vessel as a rigid body. So all the mixing, all the segregation too, in a tumbling blender occur in their cascading region. So this is the tumbling blender impart very little air. This is very important and conceptual idea. For other hand, in convective mixer, homogenization is driven by the flow formed by the motion of the impeller and depend, of course, the impeller speed. Typically, the entire power, the entire mass experience the certain amount of shear all the times because the impeller moves big amounts of powder all the time. So shear levels are controlled entirely by the speed of the impeller that drives the flow. You can reduce or you can increase the RPM of the impeller, and you will reduce the time in order to reach the content uniformity of the blend. And here a note, when, for example, when a high percentage of powder to be mixed have a strong, big cohesive characteristics, the efficient way to integrate, to incorporate the glidan is an excipient, a very important excipient that gives flowability. For example, glidan, a typical glidan in the industry is aerosil 200. So the efficiency way is improve the flow characteristic using a convective mixer, for example. So this is an example when you need to use a convective mixer, when you have a strong cohesive powder, and you can use the tumbling. Well, these are some types of tumbling blender: the symmetric double cone, the asymmetric double cone, the V-shaped, and the cubic blender. As you can see, this equipment still rotating at high speed has not a good shear, a good convection. Only dispersion and diffusion of the particle in the cascading they form is the mechanism, the main mechanism. Well, and this is a special tumbling blender because the intermediate bulk container technology is used for three functions. We will see again at the last of the presentation, but the IBC blend store and feed the tableting machine all in one. And this type of technology give us the possibility to reduce the segregation problems. We will see. And of course, these are the typical convective mixer blender, the high shear mixer granulator. You can use this type of blender when you have a very, very cohesive powder and you need transport and in free flowing powders, adding different kind of excipient. For example, a glidant, aerosol two-handed. Well, here I stop and let me know, Daniel, how following.
Yes, of course. Well, thank you, Arturo, for this first part of the presentation. There are some questions in our chat. I don't know if you can see this as well or not. Okay, we have some questions from our webinar attendees to answer. Before we go with them, let me inform that you have a survey on the screen that we will appreciate if you can answer.
Okay,
Now, you see.
I read.
Oh, excellent.
Which is the impact of API concentration on the decision on direct compression process? This is for me is the most important question. If the API have a bad attribute of flowability and compactability, and the concentration is very high, let's say 30% or more, 40, 50%, 60%, in this case, is improbable that the direct blended produce a good intermediate product. Why? Because you have few excipients to reverse, to neutralize the flowability and compactability of the API. In this case, it's probably you have to produce in granulation methodology, dry or wet. For another hand, when you have few concentration means 1% of API or less, let's say 0.5 or 0.1% of the API, psychopharmacs or high potency drugs. So in these cases, the problem is not the flowability, it's not the compactability. The problem is the obtain the good distribution of the API, and not only obtain the good distribution, but how to avoid the segregation post blending, during the tableting, during the discharge in the double cone, during the tableting per se, in the feeder or in the hopper of the tableting machine. So these are the two conditions, or big percentage of bad flowability and compactability API, or very few doses of the API. But the consequences are very different, of course. The second question is, which kind of blending are to be made with high shear mixer, and which ones with tumbling blenders? Okay, yes, of course. When the powders have free flowing characteristics, well, tumbling blenders are typical blenders, and you don't need more than this. You adjust the speed of rotation, RPM, and the time, and it's over. But when you have very cohesive powders, and you can't produce a good blend in tumbling, well, you go to high shear mixer, incorporate the powders, incorporate the glidant. This is very important to define the percentage of glidant, aerosol, carboxyl, and other, and select the good speed of rotation the impeller and the time, and surely you will obtain a blend with good flowability, good density, and probably good compactability. Okay, I think it's
excellent, excellent. Okay, one thing more by my side is now we have activated a survey on the screen. Please, we will appreciate if you could answer it. Okay, please, Mr. Arturo.
Okay, I will. I need to present the.
Okay.
To show the presentation. Let me see here. Okay. Can you see?
Not yet. Yes, yes.
Okay, okay. Well, so let me move to the here. So now we have to see the blending operational variables. These are very important because it's the mode in which we configure the operation. First of all, powder filling mode. This is not obvious because in the mode you fill the powders into the blenders. Here we are speaking about, of course, tumbling blenders. In the tumbling blenders, it's important the way you fill the powders because there are a significant difference in the powder radial mixing and powder axial mixing. We will see next. So first variable is the powder filling mode. The second, the blender low level. Let's say the occupancy is different. Is it 20% or 80%? The third variable is the rotation speed, of course. And the fourth, and the very important, is time. How many time we put the blending to operate. So 4 variables to be in mind. The first is the powder fill mode. The powder filling mode refer to the better way to incorporate the powders. If we incorporate the powders symmetrically or more symmetrically from the bottom to top, this will promote the radial mixing. And the radial mixing is very fast. It's faster than the axial mixing. The powder in the line of the axis around the container moves is very, very, very few. The mixing of the powder is very, very few, but it's not the same in the radial line. So here show a graph showing the relative standard deviation. The relative standard deviation refers to the average, to the dispersion of the content of the sampling you obtain from this equipment. You put and obtain different sampling, and then you control the content of the API and calculate the dispersion and the average. The dispersion divided average is the relative standard deviation. Here we show the standard deviation versus revolutions, or time is the same here. So what we see, that when this is the mode of loading and the radial mixing is important, the velocity of uniformity is very, very fast, and you reach levels of very few levels and indicating good uniformity. When the different weight of powder filling, in this case, is very slow. It's very low. So I know that you perhaps fill the component in this way, but try to avoid to put side to side the component, because the axial mixing is very, very low and can affect the the time you need to reach the good uniformity. The second variable is the blender load level, the occupancy. The same type of graph, RSD, percentage, versus blending time. Here we show this. The tumbling blender are rotating at 12 RPM, but the same formula at different level of load, 70%, 90%, and 30%. As you can see, when the blender is overloaded with 90%, the evolution of the uniformity or the dispersion reduces slowly, and look, after 15 minutes, still is not uniform. For other hand, when the load level is 70% or 30%, the uniformity is reached, for example, to less than 5% in 3 minutes. In 5 minutes, you have uniformity. This is, of course, due to the dead zones. When you load with too much powders, you have reduced the window, the space, the camera, where the powder expand to move into the container. So you need at least a camera of 30% empty. In this case, the powder will move adequately and the mixing will be fast. This is the impact of the level of occupancy. And the third effect of blending is the rotation speed. The same graph in this case show that when the powder load level are 60%, but the speed of rotation of a container is different, the uniformity is reached at different time. Let's see. If you configure setup at 8 RPM, this is the evolution of the dispersion. The dispersion reduced in this way. When you use 16 RPM, very fast, you need less time to obtain uniformity. So speed of rotation is a critical variable to be in mind for an adequate blending. And here we show a comparison. This graph shows the same formula, the same product, the same formula, the same batch excipient, the same batch API, but the blending made in a double cone tumbling blender and in high shear MIG 100. So it's clear that in this case, first of all, these are highly cohesive powders. This is very important to say, because in this case, the difference is very notable because tumbling blenders are not capable to reduce the dispersion because low shear in this type of blender. But look at this, when the high shear is applicable, still with high cohesive powders, you reduce the dispersion in only 2 minutes, 3 minutes. And this is a big difference, and it's an example why when we have formulation with high cohesive powder, probably we need to use a high shear mixer to a good performance. Okay, but to this point, we we speak about the generalities of blending. Let's suppose that with tumbling or with high shear, we obtain a uniform intermediate product. It's very good, it's excellent, but we have a problem. We can have a problem. The problem are post-blending problem. And I want to quote Fernando Mucio, expert in blending, solid blend from Rutgers University in New Jersey. He wrote, blend materials in a tumbling blenders does not end the processing of that blending. At some point, the blending has to be discharged from the blenders. For me, this quotation is very important and put in mind that after blending could appear problems. For example, segregation, the typical one. Segregation can occur, of course, during blending, but if the blending is okay, the most commonly occur by or during discharge from the blender. Let's suppose you discharge the powder into the tank, the double cone to the tank. Could occur during the passage through the hopper of the tablet, and could occur in the tableting machine feeders. The three possibilities. Okay. So the API segregation mechanism, so why the API segregate post-blending? Well, two main mechanisms are sieving or sifting, and the other is fluidization. We will see both cases following. Here, segregation, API segregation by sieving or sifting. Well, the smaller particle, normally the smaller particle belongs to the API, the smaller particles move through the matrix formed by the coarse particles, the larger ones, excipients, for example. Let's imagine you have a formula with API with size the order of 10 to 30 microns, and the excipients have 100 and more microns. Well, the difference is important. Not only the difference in size, the difference in shape, and the difference in density. So, four conditions must occur for the segregation during the post-blending process. First of all, difference in particle size, I say. Second, the medium size of the large particle, the coarse particle, form a matrix, and the pores, the holes between the particles, let the fine particle pass. The third question is powder with free flow, because the direct blend is a free flow, the particle free flow are separated, move independently. So small particle can move through this matrix because the API is not bind in a granule, it's free for movement. It's so simple. So, fourth condition, interparticle movement. Interparticle movement needs vibration. So, if you put a tank, a container with the power and it's static, no vibration, nothing occurs. But if you put the container in the tableting machine and tableting machine produce vibration, this could affect and produce segregation, because the vibration let the particles, the fine particles, move in a function of size, density, and shape across across the matrix formed by the coarse particle. This is the typical segregation by sifting. So a case study, look at this, powder segregation and sieving. Let's suppose that the powder blended discharge from a double cone to a container, In the discharge point, it produce a movement of a particle, so it's formed this kind of segregation. Some here in the discharge point, some with concentration of fines, probably the API, and some with coarse particle. Well, after this, we have the funnel type of the hopper of the machine, tablet machine. We have two types of powder flow, the funnel type and the mass flow type. If we have the funnel type, in the funnel type hopper, we have a stagnant layer. Here, stagnant, it's static, and the power flow flows from this part. Different is the case of the mass flow type, where the lines are from all the geometries. Well, what happens if this distribution, this now distribution, produced post blending, produced when we discharge the powder from double cone to container? If we put this over the machine, of the hopper machine of the tableting, well, look at this. The fines will deliver it first. So the sequence is, during the blend discharge from the blenders, the fine particles, API, are concentrated at the point of the charge, while the large particles are forming a matrix slide towards the periphery. Consequences: if the power flow pattern from the hopper is the funnel type, the particle API will be discharged first into the tablet machine feeders, and the first runs in the tableting will come out with high content of API. For example, in my experience, I looked this in some cases. The first runs of tableting give us tablet with 130 and 140% of API. And then in the last runs, tablet with API concentration of 80 and 85%. This is due a segregation for sifting. Okay. Now I will show you the other segregation type is fluidization. The fine particles retain more air than the coarse particle, because the fine particle have in total big area, specific area. And when the blending is discharged in the tank, the coarse particles sink to the bottom, while the fine particles remain fluidized and settle, but later. The consequence is that the fine remain on the surface, and during tableting, the last run of tableting, the last tablets will be reached in active ingredient, is opposed to the before segregation. No? For this type of segregation to occur, the particle must be 100 microns, less than 100 microns, and air source is introducing into the hopper. And look at this. This is case study. Discharge from double cone blender to a container. Well, when you discharge, this type of fluidization occurs. Free fall of dust and fine cloud formation. I saw this type of phenomenon in different laboratories, in different plants. It's very common that the discharge produce these clouds. And the clouds are formed by fine particles, normally API. So the distribution now, this is an idea. The distribution of API is fines are concentrated at H, and in the middle, low concentration of the API. So, due to the first run of tableting, the tablet will have less content, and the last runs will have more content. If the funnel pattern occurred, of course. Solution one. Well, the solution one is, of course, remove the clouds. If you remove the clouds, you avoid the segregation. This is one of the solutions. A device that avoid the formation of cloud. This dispositive is retractile, and you, in this case, you will have not segregation. But the second solution, the most effective and modern, is to use IBC technology, intermediate bulk container technology. Why? Because this technology let us not only blending the powder, but storage the powder, and then discharge, blend at the press and then tableting. So this technology avoid segregation by fluidization, avoid the segregation by fluidization, because you avoid the discharge from double con to a container, because the IBC is the blender, is the storage equipment, and is the discharge, the powder, into the hopper of the tableting machine. Here you can see the IBC connected to the hopper of the tableting machine, and of course, in this case, the probability that fluidization segregation occur is minimum, not occur. Well, this is the case. Well, I stop here.
Yeah. Well, we have, thank you, Arturo, for the exposition. It has been really interesting. Before we proceed, further question, let me inform you that activate again the survey on the screen, and that we will appreciate if you can answer. Okay. We have some questions. The first is from Mr. Tsiganov Konstantin. Depending on which one choose, one or another direct compression mixture. Depending on which one choose, one or another direct compression mixture.
Yes, the mixer, the blender are choose based on the formulation, the composition we have, and the characteristics of the powder of this formulation, and the percentage of AP that our formulation has, and the properties of this AP. If the concentration of AP is less than 30% and bigger than 5%, independently of flowability and compactability, I believe that you conduct tumbling blender, because you will use a very good excipient, cellulose, lactose, phosphate, carbonates, starches, etc., that will give you flowability and compactability. And because you have no more than 30% and more than 5% of AP, this blend will perform very good in tableting process. But if you have API with more than 30%, let's suppose 40%, 5% of API, and this API has bad flowability, is very cohesive, or bad compactability, so it's probable you need to use convective, high shear machines, blenders. Of course, you could try to use tumbling blenders and try, but probably you can't find the adequate condition. So I think the better way is to produce to blend with the high share. For other hand, if the percentage of API is lower than 5, lower than 1%, you have a problem. The problem are two. First of all, how to obtain a uniform blending, and how to avoid the segregation post-blending. So this is a problem. You have no problem with flowability. You have no problem with compactability. You have a problem with content uniformity. This is the only problem you have. So in these cases, in my experience as a developer, when I have a formulation with 1%, 0.5%, I try to pre-blending. Pre-blending are blending with parts of the formulation, geometric blending or non-geometric blending, and progress to the final blending. In this case, you can obtain a product, a mix that is uniform and not tend to segregate. So, in my opinion, when you have low dose or very low dose, try to use tumbling blenders, but using the concept of pre-blending by geometric or non-geometric. Two are very good alternatives.
Okay. One question more is the BIN, the sieving step calibration is also a critical phase in the preparation of the blend?
Yes. If you remember, in the complete line, of direct compression is the milling equipment, the blender, the tableting machine, and the coater. Why? First of all, we milling in a conical mill, because raw materials, not only the excipients, but the API too, comes with lumps, with agglomerates, bigs. I saw in cases very big lumps, the order of centimeters. So you need to reduce this size to the order of microns. So you need to put a milling step in order that to the addition of the powder to the blender is the particle with fine sizes.
Excellent. Okay. Well, we have between hands one more question from Mr. Mohammad Al-Dasuki. He said, when I should use roller compactor machine.
Okay, a roller compacting machine is an alternative to direct compression blending. In the case you can use direct compression because the flowability, because the density, or because the compactability are bad, and you can obtain a intermediate product with good attributes of flowability, compactability, density, and uniform, well, you have to granulate. Of course, the first alternative to granulate is the granulation in roller compaction. We will see this procedure the next webinar, the fourth webinar. We will try specifically the dry granulation, and we will give example for this technology. But of course, you have to granulate when direct compression is not possible.
We would like to remind that the next webinar will be on June 21. This fourth webinar will be related the dry granulation line, and during the following days we will launch the inscription so that you can register. I reminded that we have activated a survey on the screen that we appreciate if you can answer. Thanks everybody for participating on this webinar. We have received a lot of questions, but I say before, the question that has not been answered today, we will do it by email. Okay, it has been a pleasure to share your knowledge with us, Professor, and we look forward to seeing you again during our next webinar. Thank you very much, and everyone, and have a nice day.
Thank you very much.